The guitar has been a staple of modern music for centuries. It is a six-string instrument that is used in almost every genre of music, and is also seen in almost every part of the world and many world cultures. Well, today I'm going to explain this science. My name is Derek De La Cruz, and this is the science and applications of the acoustic guitar. Let's get into it. The guitar originated in Spain early in the 16th century, deriving from a late medieval instrument called the guitarra latina, which was an instrument with a wasted body and 4 strings. It was closely related to the vihuela, a guitar-shaped instrument also played in Spain. Since then, it has been incorporated in many world cultures. Names such as Wes Montgomery, Django Reinhardt, and Chuck Berry revolutionized the use of the guitar in jazz and blues, while names such as Jimi Hendrix, Jimmy Page, and Eric Clapton revolutionized the use of guitar in rock and roll. Even virtual personas such as Noodle, Yui Hirasawa, and KK Slider are associated with the guitar. This presentation will focus on the science of guitar and how its components function together. The guitar model that will be used in this presentation is the Fender FA125 Dreadnought acoustic guitar. Before we go into the science of the guitar, we have to discuss the science of waves. A wave is a disturbance of a field or medium that was initially in equilibrium, and ripples in space are created around it and the path where it travels. There are 2 major types of waves commonly studied: mechanical waves, which are vibrations, and electromagnetic waves, which are light. There are other waves, such as gravitational waves, but for the sake of this presentation, we're going to be focusing on these 2. More specifically, we're going to focus on mechanical waves, because the waves that the guitar creates are mechanical waves. In a wave, the crest is the highest point and the trough is the lowest point. The amplitude is the distance from the maximum or minimum to the midline of the wave, and this is measured in meters, and this also corresponds with loudness, which is measured in decibels. The wavelength, represented by the symbol lambda, is the length of one wave measured in meters. Frequency is the number of waves in a second, which is measured in hertz, and period is the time for one wave to pass a point, measured in seconds. Frequency and period are inversely proportional concepts. So period can be found by dividing 1 by frequency, and frequency can be found by dividing 1 by period. And lastly, wave speed is just the speed of the wave, measured in meters per second, and it's found by multiplying the wavelength by frequency, or dividing the wavelength by period. Remember, they are inversely proportional. Electromagnetic waves are the waves of the electromagnetic field. They are emitted by charged particles undergoing acceleration. And the chart that we see here is the electromagnetic spectrum. It has waves with the shortest wavelengths, such as gamma rays, and then waves with the longest wavelengths, such as radio waves. And that little section in the center with color is visible light. There are 2 things to note here. First of all, high-frequency waves such as gamma rays can damage cells, hence why it's called gamma radiation. And visible light bounces off surfaces into our eyes, and this is what we perceive as color. Some additional things to note about electromagnetic waves is they can travel through a vacuum, and they travel at 3 times 10 to the 8th meters per second, which is the speed of light. And they also act like particles called photons, and this duality of acting as a wave and a particle is a fundamental idea of quantum mechanics, which is called wave-particle duality. Electromagnetic waves are created in stars, because stars are high-heat, high-pressure environments, especially in the core, and nuclear fusion occurs in the core, causing energy and light to be created. But it's important to note that not all electromagnetic waves are created equally in stars. The other kind of major wave studied are mechanical waves. Mechanical waves vibrate the air around them, and they require a medium in order to travel. So what this means is they cannot travel through the vacuum of space, unlike electromagnetic waves which can. And they can also only exist if equilibrium is disturbed. Mechanical waves travel in 2 ways: transverse, which is traveling at right angles to create crests and troughs, similar to sine and cosine waves we see in graphs and functions, and longitudinal waves, which means they travel in the direction of propagation, and they do this via the compression of the medium. And this is how sound waves travel, which are the waves that we are concerned with in the analysis of the guitar. Some mechanical waves are audible, and this depends on the pitch, measured in hertz, and the loudness, measured in decibels. In terms of energy transfers from potential to kinetic in the initial disturbance, and the vibration of particles accelerate nearby particles, increasing kinetic and mechanical energy, which is potential plus kinetic. Let's start talking about the anatomy of the guitar. The very top of the guitar is referred to the head or headstock, which consists of 6 tuning pegs, which affect the pitch of the strings. From there, there's a nut that disconnects the neck and the head, and 20 frets on the guitar. This layer of frets is called the fretboard. There are 6 strings, steel in our case, and the neck joint connects the neck to the body. Other parts to note is the bridge and the saddle at the very bottom, and the sound hole in the center. Let's talk about the measurements of the guitar. Once again, this is a Fender FA125 dreadnought. There are 6 steel strings and 20 frets. The body is 51 centimeters tall, the neck is 46 centimeters tall with 10 centimeters sticking into the body, and the headstock is 18 centimeters tall. This means that the whole guitar is 105 centimeters tall. The sound hole in the center is 10 centimeters in diameter, which makes it 5 centimeters in radius. The nut width, which is the part on the top, is 1.69 inches, or 43 millimeters. The body's width is 10.5 centimeters, and the volume of the body's interior is 253 cubic inches, which is also 0.146 cubic feet, or 0.004 cubic meters. The scale length, which is the distance of the nut to the 12th fret times 2, is 25.3 inches, or 0.64 meters. And the string length, which is just the length of the string, is 25.75 inches, or 0.65 meters. The guitar works because of the guitar's body. The sound hole is critical to this. When the strings are plucked, the sound waves travel through the sound hole into the body. From there, the air particles that are in the body vibrate from the mechanical waves, amplifying the sound and giving the guitar the rich sound that we're all familiar with. If the air was more dense, then the sound would travel farther, and if the air was less dense, the sound would travel less far. And in a vacuum, the guitar wouldn't be heard at all, because all mechanical waves need a medium, and they would have no medium to travel through. The guitar has 6 tunable steel strings. The gauges, or thicknesses, of the strings are as follows. The thickest one is 0.046 inches, which is the E string. Then the A string is 0.036 inches. The G string is 0.07 inches. The B string is 0.013 inches. And the thinnest string, the high E string, is 0.01 inches. The wound just means that the string has been wrapped to make it thinner, while the playing just means it hasn't. The open notes, or the notes that are played without pressing any frets on the strings, from highest to lowest pitch are as follows. E4, which is 329.63 Hz, B3, which is 246.94 Hz, G3, which is 196 Hz, G3, which is 146.83 Hz, A2, which is 110 Hz, and E2, which is 82.41 Hz. The numbers after the name of the notes represent the octave. The sound waves, like any other mechanical wave in the air, travel at approximately 340 meters per second. This table shows a clear correlation between note pitch and string thickness. Thicker strings play lower notes and thinner strings play higher notes. This is also not a linear relationship. The material of the string is also relevant. Steel makes the string louder, sharper, and more resistant to heat than the alternate choice, nylon. It allows the neck to be longer, letting players play higher notes on the fretboard and doesn't require players to retune as much. Thus, steel is a much more popular option amongst guitarists. However, a disadvantage with these types of strings is that they are harder physically, meaning that they can hurt the player's fingers more easily. Nylon, on the other choice, is softer and easier on the fingers, making it better for longer periods of playing. However, they are quieter than steel strings, and they also can be stretched as far as steel strings, meaning that the neck of the nylon guitars are shorter, reducing the amount of playable notes. Essentially, nylon strings are good for beginners, but if a person wants to continue to pursue guitar, they must make the switch to steel strings. The tension of a string also affects pitch. Higher tension plays higher notes, and lower tension plays lower notes. In essence, this is how tuning works. When the tuning knobs are turned, tension is either increased or decreased, changing the pitch of an open note. A technique that exploits this string tension is called neck bending. Neck bending occurs when the player presses on the back of the guitar headstock. This very slightly bends the neck, decreasing the distance from the bridge to the nut, and decreasing the tension applied. As a result, this flattens or lowers the notes' pitches. And then the notes sharpen or raise in pitch again when the force on the headstock is released. Take a look. Constant playing and applied tension very slowly wears down the string, reducing its Young's modulus, a measurement of stiffness. As stiffness decreases, the material becomes more elastic, making it looser and detuning the string, and it also makes it less capable of staying in tune. However, this problem is easily fixed by binding strings, and the damage occurs over many years of playing. A harmonic frequency is a frequency that is part of the harmonic series, which is referred to as the overtone series in music theory. This series is a sequence in which each frequency is an integer multiple of the fundamental frequency of the open note. So what does this mean? Well, let's take a look at the diagram in the bottom right. We see we have the first harmonic, which is the length of the full string. The second harmonic, we see that the wave is cut in half. The third harmonic, the wave is cut in thirds. The fourth harmonic, the wave is cut in fourths. On guitar, there are certain areas that can be lightly pressed that can play the overtones, and these areas are called notes. This technique is called natural harmonics. The second harmonic is the 12th fret, the third harmonic is the 7th fret, and the fourth harmonic is the 5th fret. Anything past this is difficult and out of tune. Take a look at what this means. You hear those lighter notes? Those are overtones. The intervals on the natural harmonics of music theory is the octave, perfect fifth, and perfect fourth. Once again, the fundamental is the main note. An example of this is that the fundamental is E2, the natural harmonics respectively are E3, B3, and E4. These overtones occur because of string vibration. Overtones are always played when any note or any string is played, and the brain is trained to not hear the overtones. So what this technically means is every note is also a chord, and this also means that millions of overtones could be played on a single string that is large enough and with enough energy. And once again, placing your finger over these certain frets amplify these overtones. The guitar is a very beautiful and powerful instrument that uses a lot of science. Learning a musical instrument is beneficial because it helps stimulate the body and the mind. The guitar is no different, and the satisfaction of learning a new song or a new tab makes anyone happy. It's an amazing instrument and is associated with thousands of musicians, songs, and albums, young and old. And let's take a minute to really appreciate the science of guitar and how complex it truly is. Thank you, everybody, and thank you, Mr. Block.
Skies above the city painted a lovely